Hello everyone, welcome to the course on Electrical and Electronics Engineering. In this session, we are going to see the fundamentals of three-phase AC systems, three-phase winding connections, and in that how the line and phase voltage as well as line and phase current are related with each other in case of a star and delta connected uh, three-phase winding systems.
In three-phase AC circuits, there are two possible connections. One is star or the Y connection and the other is delta or mesh connection. Each of these connections is governed by characteristic equation which relates the current and voltages. Here in this analysis, phasor diagram plays a vital role. First, we will see the star connected systems. Here, as we see the three similar ends of a three-phase coils, they are joined to form a common point. Such a point is called neutral point or the star point. Then the free ends of the three-phase coils, these three ends will operate at the specific potential with respect to the potential at the star point. Here the wires are drawn from the three free ends for connecting to the loads. Okay, the free end. And we have a three-phase four-wire system as shown here and three-phase three-wire system also. If you include the neutral, the star point also, it's a four-wire system, else it's a three-wire system. We will analyze the three-wire system here, three-phase three-wire. We are going to find the relationship between line voltage and line current and phase voltage and phase current. And finally, we will find the power equation. Here, if you see this diagram, so we consider R, B and Y are the three phases. So the phase voltage across these windings are ER, EB and EY. The current flowing is phase current, that is IR, IB and IY. The line voltages, okay, across the free ends are, okay, line voltage is nothing but V R Y until here. Then across these free ends VYB, and from the first and the last one it is VRB. Okay, and the line currents is the line flowing in the free ends IL1, IL2 and IL3. In a balanced system, if you take this phase voltages ER, EY, EB is equal to EP, and phase current IR, IY, IB is equal to IP. Similarly, line voltage VRY equal to VYB equal to VBR equal to VL. Similarly, line current IL1, IL2 equal to IL3, that is equal to IL. Now we are going to draw the phasor diagram. So we know that it's connected in the form of inverted Y, right? So what you do, you take this is R, right? We invert a little bit here, ER, EY, EB. And opposite to each of the positive potential, there is a negative. ER opposite minus ER, EY opposite minus EY, EB opposite minus EB. So if you consider and phase line voltages, this is phase voltage. Line voltage will be in the middle, okay, in the middle of each of them. So RY, YB and BR.
Coming to the current relationship, we apply Kirchhoff's current law at nodes R1, Y1 and B1. We get IR equal to IL1, IY equal to IL2 and IB equal to IL3. This means that in a balanced star connected systems, the phase current is equal to the line current, IP equal to IL. This is very important in star connected system. Phase current and line current are both equal. Now we need to analyze the voltage relationship. For that, apply the Kirchhoff's voltage law to the loop consisting of EY, ER and VRY. So we have ER minus EY equal to VRY. Using the parallelogram law, we take modulus of VRY is equal to root of ER square plus Ey square plus 2 ER Ey cos of the angle between the ER and Ey. That is here how much total 360 degree is divided by 6. So 60 degree. Cos 60 is what? It is 1 by 2. All the we have considered, right, this ER, EY, EB as EP. That is, they are the phase voltages. So if you substitute that, we come to know that it is EP into root 3, because EP square plus EP square plus again this half get cancelled, 1 EP square. So 3 EP square will come. Similarly, if we find across the other two terminals also, that is EY minus EB equal to VYB, and EB minus ER is VBR. In that case, VYB is equal to root 3 EP. Similarly, VBR equal to root 3 EP. So what implies? These are the line voltage. Line voltage is nothing but root 3 times the phase voltage. Coming to the power relationship, cos phi is the power factor of the system. So power consumed in one phase is the EP IP into cos phi. In a three phases, it is three times of that. So we substitute what is EP here. It is VL by root 3. What is IP? It is IL. So it is 3 can be written as root 3 into root 3. So one of the root 3 get cancelled. So power consumed is root 3 times VLIL cos phi, which is in watts. Now we are going to see about delta connected system. Here the dissimilar ends, okay, of three phase coils, they are connected together to form a mesh. Wires are drawn from each junction for connecting the load. We can connect only three phase loads as there is no fourth wire available here. Now let us analyze this connection. This system is a balanced one. Here the currents and voltage will be balanced. The same notation that we used in star connections are used here. This is B, right? So it is EB, EY and AR across these windings, and the current is IB. Okay, the B1 across this B1, B2 we are marking, and here it is IY, Y1, Y2 we are marking, and here it is IR. And the line current are supposed to be IL1, IL2, IL3, and the line voltages is VBR. This is R is taken, and Y, and this is VY, and this end is B, VYB, RYB, right? Now we will analyze the relationship between phase voltage and current, and line voltage and current also. So for that we draw the phasor diagram. Here the phasor diagram comes in this way. Previously it was like this, right? Okay, or we can take in this way itself. Fine, inverted Y only they have taken. Yes. Now we have to take the diagram as shown here. So we can see that here it is IB, IR and IY. Okay. Then opposite to that will be minus IB, minus IR and IY. And here if you join together, it is what? IL3. IL3 is across B and Y. And similarly, this is IL2 across IL2 across Y and R, right? Similarly, B and R, it is IL1. So if you see the phase voltages ER, EY, EB equal to EP, IR, IY, IP equal to IP, that is phase current, and line voltages VRY equal to VYB equal to VBR, that is VL. Line current is IL1, IL2, IL3 equal to IL. So to find the voltage relationship, apply the case KVL at the loop, okay, consisting of this. In this loop, we are going to consider what is that loop? ER and E, ER and what is the loop here? This loop only, ER and VRY. So we found that ER equal to VRY, and EY equal to VYB, and EB is going to be equal to EB is going to be equal to This complete, right? VBR. So EP equal to VL, that is this phase voltage is equal to line voltage in delta connected system. But in star, it only phase current and line current are equal. So coming to the current relationship, we apply the KCL at the junction, and we apply the KCL at the junction of where we are applying the KCL. It is R1 and B2. Where is that R1 and B2? Here. This is R1 and B2. In this junction, if you apply KCL, what happens? IR equal to IR, right? Minus IB. It's coming out. Minus IB equal to IL1. Or we can write in this way, incoming current equal to outgoing current, right? IR1 equal to IB plus IL1. From that IL1 we can write IR minus IB. Referring to the phasor diagram and applying this parallelogram law, okay, IL1, how we can write? IL1 is nothing but IR square plus IB square plus 2 IR IB cos complete angle. Here it is 60 degree. So if we apply the cos 60, that is 1 by 2, we get IL1 equal to root 3 times IP. Similarly, we have to find across the other three junctions, and we come to know that line current equal to root 3 times the phase current. Coming to the power relationship, phi is, cos phi is the power factor. Power per phase is EP into IP cos phi, and the total power for all the three phases is 3 times of that. We substitute what is the phase current and phase voltage and current. Phase voltage is equal to line voltage, but phase current is what we have found, line current divided by root 3. So we get the phase to power to be constant, root 3 VL IL cos phi watts. Is it same? Okay. Now we will compare these two systems. In star connected system, there is a common point called as neutral or a star point. It can be earth, but here in delta connection, there is no neutral point. In star connected system, we can have three phase, three wire system, also three phase, four wire system. But in delta connection, only three phase, three wire system is possible. Here in star, the line current is equal to phase current, but in delta, line voltage is equal to phase voltage. Okay, but in star, the line voltage is root 3 times the phase voltage, or we can say the vice versa. Similarly, in delta, the line current is root 3 times the phase current, or we can write in other way. Hope you understood the analysis of three-phase AC systems. With this, the Unit 1 electric circuits consisting of DC circuits as well as AC circuits fundamental comes to an end. Hope you enjoy the session. We will meet in the next section, which covers the second unit. Thank you, everyone.